The enigmatic and unpredictable nature of space has perpetually captivated the human imagination. However, the vast expanse beyond our world proved to be an unforgiving and hazardous frontier, where frigid temperatures, fatal radiation, and a hard vacuum created insurmountable challenges to our direct exploration of other planets and stars. It is for this reason that we engineered machines, designed to endure the extreme conditions of celestial bodies, and today, you will join them on an incredible expedition. Our expedition starts with Mars, the most thoroughly examined planet in our solar system. We will then journey to the spectacular rings of Saturn and uncover the fate of the probes sent to study them. From the myriad of known moons, we'll visit the hazy world of Titan and the volcanic landscape of Io. Following these tireless cosmic explorers, we will venture to the far reaches of the solar system to see the dark and mysterious Pluto. After that, a profound voyage through the interstellar void awaits us, traveling alongside the intrepid Voyager probes to instantly cross several light years and reach the remarkable Alpha Centauri system. Our exploration will conclude with a visit to the closest known star, so prepare yourself, as our journey is about to begin. It is widely believed that several billion years in the past, Mars looked very much like this. The planet was enveloped in a dense carbon dioxide atmosphere that retained heat and moisture. This allowed numerous rivers to flow across its surface, and a large part of the northern hemisphere was submerged in water. All of this, however, was fated to vanish, leaving behind only geological echoes in the stone. The prevailing theory suggests that over hundreds of millions of years, the weak and unstable magnetic field of Mars failed to shield it from the relentless solar wind. As a result, the atmosphere progressively thinned, and lighter gases like oxygen escaped into space from the upper layers. Now all that remains of the red planet's once abundant water is a thin coating of orange dust and vast stretches of permafrost. To truly grasp what is occurring on Mars today, we must first examine its interior. Thanks to the sensitive seismographs on the InSight lander, which studied the planet's internal structure for many years, scientists have gained a clear understanding of the processes happening deep inside. At the very center of Mars is a large, massive core composed of iron, sulfur, and nickel. Its radius is more than half that of the planet, and due to immense pressure, most of this core is solid, which means it cannot generate a stable magnetic field. The core is surrounded by a layer of molten mantle that is approximately 1,000 kilometers thick. Its composition is not uniform. The lower layers contain oxides of various metals, while the upper sections are made of olivine and silicates. This mantle is enclosed by a massive crust with an average depth estimated at around 50 kilometers, making it 5 to 10 times thicker than Earth's oceanic lithosphere, and comparable to the thickness of our planet's continental crust. The crust of Mars's northern hemisphere consists mainly of andesite, while the southern hemisphere's is primarily basalt, suggesting they formed in different geological eras. Decades of observation have provided us with hundreds of thousands of images of the Martian surface. By combining them, we have created a detailed map of the planet that showcases countless features. While some are quite small, others stretch for thousands of kilometers and are visible from Earth through a telescope. One of the most breathtaking regions is Valles Marineris, a network of intertwined canyons extending 4,500 kilometers along the planet's equator, its western section deeply cutting into the vast volcanic plateau of Tharsis. Our descent into this great rift will commence almost at the center of this giant plateau. within the unique and mysterious region known as Noctis Labyrinthus. This is a chaotic terrain that stretches 1,200 kilometers from west to east. Here, numerous deep fissures with steep edges intersect repeatedly, fracturing the planet's surface into irregular blocks. Their upper layers are composed of softer, lighter, and heavily eroded deposits, while the base is formed by solid bedrock. For billions of years, the slopes of the plateau were washed by water flows that converged to the east. Evidence of this includes signs of deep water erosion found at the bottom of most fissures, as well as the layered structure of the slopes and signs of landslides. Furthermore, spectral analysis shows that this region is rich in minerals that require liquid water to form, such as hematite, opals, and iron sulfates. Observations also indicate that Noctis Labyrinthus is periodically shrouded in dense fog, which makes it one of the most humid regions on Mars. It is thought that water contained in the soil evaporates into the thin air during the day. When temperatures drop, this water condenses into microscopic ice crystals that slowly settle on the surface, creating a delicate layer of frost. As we continue eastward, the intricate network of fissures in Noctis Labyrinthus gradually transitions into a system of giant canyons. Over billions of years, these features have been carved by powerful water flows, winds, and sandstorms. Eventually, we will arrive at a colossal abyss, the deepest point in Valles Marineris. Located 11 kilometers below the surrounding plateaus, calculations suggest that in ancient times, this chasm was a narrow, elongated lake with a volume comparable to Earth's Black Sea. This region is considered one of the most promising targets for future research. The soil and the bottom of the abyss may contain traces of ancient organisms, and its slopes serve as a detailed record of the planet's geological history, holding significant scientific value. Continuing our journey through the canyon, you will see that it gradually loses its steepness and smoothly merges into a gentle valley, which was likely formed by sediment from Valles Marineris. On our own planet, you can find comparable geological structures in the deltas of great rivers like the Amazon or the Nile. With that, we have just examined one of the most magnificent and apparent signs of ancient Martian water, a region that has only ever been observed from orbit, where no rover has yet made tracks. To get a closer look at Mars, we need to venture far to the east of this location. After a journey of several thousand kilometers across forbidding stony deserts, we arrive at the vast crater known as Gale. 8 billion years ago, a colossal asteroid impacted this spot, carving out a deep, circular basin that spans 154 kilometers in diameter. At its heart rises Mount Sharp, a massive, irregularly shaped mountain built from layers of sedimentary rock, which was likely once a central island within a large round lake. Gale Crater is now renowned for being the landing site of the Curiosity rover. The story of this remarkable mission started almost 11 years ago, on August 6, 2012, when this autonomous scientific vehicle, a testament to human ingenuity, touched down on the Martian surface. Its primary objectives were to analyze the planet's climate and geology, while searching for traces of water and any potential signs of life. Almost right away, the rover confirmed that Mars once had a much wetter environment than it does at present. The initial images sent back to Earth vividly depicted Peace Valles, a valley clearly sculpted by a powerful flow of water. This specific site, which was named Yellowknife Bay, stands as one of the planet's most compelling examples of water erosion. From there, Curiosity traveled east, soon arriving at a sandy depression named Rock Nest. It was here that the rover collected its first soil sample, revealing that the Martian ground contained approximately 3% water. Curiosity then shifted its course to the southwest, embarking on a long traverse through the barren, rocky terrain of the Glenelg region, where ceaseless winds have scoured away sedimentary layers to expose bedrock that is over 4 billion years old. Carefully navigating up rocky inclines, Curiosity made its way to the western perimeter of the Bagnold Dunes, where it examined sedimentary rocks that are, geologically speaking, relatively young. Leaving the desert behind, the rover pivoted south to begin the slow, challenging climb up a mountain ridge known as Vera Rubin Ridge. During this ascent, the terrain under its wheels transitioned from sand and silica to hematite, an iron oxide that can only form in the presence of liquid water, confirming the region once had a much wetter climate. Having endured for over 3,000 Martian days, far exceeding its originally planned mission length by about 5 times, Curiosity has proven to be an icon of resilience. It has journeyed nearly 30 kilometers across the severe Martian landscape, collected 28 distinct soil samples, and its instruments have detected not only water, but also organic molecules like benzene and aromatic hydrocarbons, all while its cameras have captured thousands of stunning images and videos for us. Leaving this tenacious rover to its work, our journey continues southwest toward Hellas Planitia, one of the most massive impact craters on Mars. The prevailing theory is that about 4 billion years ago, a gigantic asteroid with a radius of around 50 kilometers slammed into the planet at an immense velocity. The resulting cataclysmic blast gouged out a crater roughly 2,300 kilometers wide and launched millions of tons of shattered rock far beyond its rim. It is even possible that some of these ejected fragments escaped into space before eventually falling back to the planet's surface, hundreds or perhaps thousands of kilometers from the initial point of impact. Back then, Mars was probably a far more hospitable and comfortable world than the one we know today. The colossal basin created by the collision filled with water, forming a great lake or perhaps even an inland sea. Over the course of billions of years, this body of water gradually vanished, leaving behind the immense crater we can observe now, which descends to a depth of over 7 kilometers. Although the basin's floor might look flat and featureless from a great distance, this appearance is deceiving. In truth, the surface is a network of ridges and fractures, which scientists believe were formed by the movement of ice layers beneath the ground, creating a landscape similar to what you might find in Earth's Arctic regions. Because of its profound depth, the atmospheric pressure within Hellas Planitia is about double the Martian average, which gives rise to some strange weather patterns. Periodically, a thick, misty haze develops over the basin. While the winds manage to carry some of this haze away, what remains either dissipates quickly in the thin air or settles as frost upon the frozen rocks. During the Martian winter, the entire plain becomes blanketed in frost, making it visible from Earth as a large, bright patch on the planet's surface. It wasn't until the close of the 20th century that scientists were able to determine the true nature of this enigmatic region. Our final point of interest now takes us north to Jezero Crater, a location that, in its distant past, was a large lake with water flowing through it. This ancient lake was fed by the Sava River from the north and the Neretva River from the west. The remnants of these Martian waterways are still etched into the planet's surface today, visible as layered river sediments and significant washout channels in the crater's mountainous walls. It was one such area that became a prime objective for the Perseverance rover, which successfully landed in Jezero Crater on February 18, 2021. The initial plan called for the rover to investigate a region named Three Forks, located in the Neretva River Valley. However, unforeseen weather conditions caused the landing site to shift 1.7 kilometers to the southeast. This placed an expanse of treacherous, impassable sands known as Seta directly between the rover and its primary scientific target, presenting an immediate and significant challenge to the mission. This was the first time we saw the Ingenuity helicopter truly demonstrate its full potential, delivering a sweeping panorama of an ancient delta and an exclusive image of the Kodiak Plateau, which was situated 2.3 kilometers from the rover's touchdown point. Once Perseverance had adjusted to its new environment and completed an initial survey, it embarked on a formidable trek around the harsh desert separating it from its objective, a mission that stands as a testament to our technological advancement and relentless spirit of exploration. As Perseverance navigated south, skirting the boundary of a region known as Seta, it would pause periodically to gather samples of Martian soil, while the Ingenuity helicopter executed one flight after another, providing you with breathtaking views of Mars from angles we had never before seen. The initial strategy called for the rover to cross the crater floor, bypass the southern part of Seta, and follow a rocky ridge north to the delta within 168 Martian days. But as you can imagine, the terrain was far more treacherous than anticipated, forcing Perseverance to double back to its landing site before striking out across the desert toward its destination. After a grueling and protracted voyage, Perseverance made a gradual turn to the west and finally arrived at the delta, where it began its detailed exploration in April of 2022, on the 413th Martian day of the mission. To give you a sense of its accomplishments so far, the rover has journeyed more than 18 kilometers over the unforgiving Martian landscape, collected 15 distinct soil samples, and transmitted over 166,000 images, along with gigabytes of data from its full suite of sensors. Furthermore, an onboard instrument called MOXIE successfully generated about 100 grams of pure oxygen directly from the carbon dioxide-rich Martian atmosphere, a breakthrough that opens up new possibilities for future human colonization. At the same time, the InSight lander detected several Marsquakes, confirming the planet is geologically active, while the flights of Ingenuity have definitively proven how invaluable aerial vehicles are for research and reconnaissance on other worlds. When you look beyond the endless desert landscapes and rocky fields, you'll find that Perseverance also turns its cameras toward the Martian night sky. For example, it has captured images where one of the tiny white specks of light is Deimos, one of Mars's 2 moons. More dramatically, the rover recently recorded the moment Phobos passed in front of the Sun, an observation that was not only visually stunning, but also furnished astronomers with an abundance of crucial scientific data. As you may know, Mars has 2 moons, Phobos and Deimos, which are quite different from our own. They are small, lumpy, and irregularly shaped celestial bodies. Spectral analysis suggests their composition is very similar to carbonaceous asteroids, yet their precise origin is still a topic of intense scientific debate. One leading theory proposes they are the shattered remains of a body captured from the asteroid belt billions of years ago, while an alternative hypothesis suggests they might be the surviving fragments of a massive protoplanetary object that was destroyed during the chaotic formation of the solar system. Let's take a closer look at Phobos, the larger of the 2 moons. It circles Mars above its equator at a proximity about 64 times closer than the distance between the Earth and our moon. In fact, some of our own satellites orbit 3 to 5 times higher. Despite this closeness, Phobos is so tiny that from the Martian surface it appears 3 times smaller than our moon does to us. Perhaps its most astonishing feature is its low average density of just 1.9 grams per cubic centimeter, which implies that up to 40% of its interior is empty space, leading scientists to believe it may be a collection of fragments held together only by gravity. The 2 moons are also on dramatically different long-term trajectories. Tidal forces are causing Phobos to slowly spiral inward, losing about 1.8 meters of altitude every century. Projections show that in 30 to 50 million years it will be ripped to shreds by the planet's gravity, with its debris raining down on the surface. Deimos, however, is moving in the opposite direction, orbiting in a nearly perfect circle at a radius of about 23,500 kilometers and gradually receding. It is expected to break free from Martian gravity entirely in a few million years. If you were standing on Mars looking at Deimos, you would find it to be an exceptionally dark object, with a surface that soaks up nearly 93% of all incident sunlight. It is so small that its disk is invisible to the naked eye, appearing instead as a particularly bright point of light. Interestingly, due to its orbital characteristics relative to Mars's rotation, it seems to travel backward across the sky compared to Phobos, even though both moons are actually orbiting the planet in the same direction. Now, if we shift our focus to Saturn, you'll discover that its famous rings lack any sharp, defined edges. While the main, visible portion spans about 280,000 kilometers, incredibly faint extensions of dust and gas stretch much farther out, with some estimates putting their diameter at up to 16 million kilometers. Despite this impressive size, the total mass of the entire ring system is quite small on a cosmic scale, estimated at 3 times 10 to the power of -1/19th power kilograms, or roughly 2,000 times less than the mass of our moon. The solid particles making up the rings occupy only about 3% of the system's total volume. The remainder is a near vacuum, filled with trace amounts of gas and dust. We typically refer to several major rings, but if you look through a powerful telescope, you will see that each one is actually a collection of countless smaller concentric ringlets. These are separated by narrow gaps, some hundreds of kilometers across, all carved out by the complex gravitational pulls of Saturn and its many moons. And while the main disk reflects far more sunlight than the planet itself, some of these rings are so faint they are nearly impossible for you to observe. For example, the ring closest to the planet is composed of extremely fine particles of water ice and frozen methane. Its outer edge is estimated to be 16,500 kilometers from Saturn's conventional surface, while its inner portion merges seamlessly into the planet's atmosphere without a defined boundary. Following this is the C ring, a significantly brighter and more massive band with a width of about 17,500 kilometers. It is populated by cosmic bodies up to 2 meters in size, which, despite their number, constitute only 0.33% of the disk's total mass. The most luminous and easily seen part of the disk is located farther out and is known as the B ring. This feature begins approximately 34,000 kilometers from the gas giant's surface, and its width extends for 25,000 kilometers. While the majority of this ring has a thickness of just 5 to 10 meters, its outermost section forms a vertical wall that rises to a height of 2.5 kilometers. Finally, the A ring, the last of the clearly visible rings, starts 64,000 kilometers from the planet and spans about 14,600 kilometers. It is composed not just of sizable ice fragments over 10 meters across, but also contains moons such as Pan and Daphnis, which lends support to the idea that the rings were formed from a disintegrated icy moon. Beyond these main structures lie the F, G, and E rings, which are almost invisible and are made up of cosmic dust and diffuse gas. The majority of Saturn's large moons have an active relationship with the rings. If you were to travel to a distance of 179,000 kilometers into the region of the E ring, you would encounter a celestial body named Enceladus. With a diameter of only 500 kilometers, it isn't among the gas giant's largest moons, but it holds immense interest for other compelling reasons. Enceladus is distinguished as one of the few bodies in our solar system that displays unambiguous cryovolcanic activity. Analysis of its observed plumes strongly suggests that a liquid water ocean is hidden beneath its icy surface. Thermal models indicate that this ocean's temperature ranges from minus 45 degrees Celsius in its upper layers to 0 degrees in its lower depths. Thanks to a high concentration of dissolved salts and ammonia, the ocean remains liquid despite the sub-zero temperatures, all while being covered by an ice crust approximately 2 kilometers thick. The atmosphere of Enceladus is exceptionally thin, comprised of 91% water vapor, along with nitrogen, carbon dioxide, and methane. This gaseous shell is constantly renewed by powerful geysers that erupt from cracks in the moon's icy crust. However, the moon's gravity is too weak to retain this atmosphere, so its upper regions continuously shed particles that replenish the E-ring. At the same time, Enceladus captures material from the surrounding space, thereby maintaining a curious balance. It is also understood that the moon's geyser activity is linked to its orbital path, as tidal forces from Saturn likely warp the icy crust, creating the fissures that allow for these eruptions. At a much greater distance of about 300,000 kilometers, you will find Tethys, the fifth largest and fifth most massive of Saturn's moons. It is distinguished by the fact that it shares its orbit with two other objects, Telesto and Calypso, which are situated at stable gravitational locations known as Lagrange points. Telesto orbits 60 degrees ahead of Tethys, while Calypso trails behind by the same angle. Unlike the large, spherical Tethys, these companion bodies are small and irregularly shaped, with diameters ranging from 20 to 30 kilometers, and a combined mass of only a few trillion tons. Orbital simulations suggest that Calypso and Telesto could not have formed in the same orbit as the much more massive Tethys, indicating they settled into these positions much later. Tethys itself is a celestial body with a diameter of around 1,060 kilometers, made up mostly of water ice with a small amount of rocky material mixed in. The most striking feature of its terrain is the enormous impact crater Odysseus, which measures about 450 kilometers across, nearly half the diameter of Tethys itself, and is up to 3 kilometers deep. Another incredible formation on Tethys's surface is the Ithaca Chasma, a canyon that stretches for 2,000 kilometers, or about 1/3 of the moon's circumference, and reaches widths of up to 100 kilometers. Its depth varies from 3 to 5 kilometers, and its floor is marked by numerous smaller craters and irregularities. There are two leading theories regarding the formation of this immense canyon. One idea proposes that the chasm was created when Tethys's internal ocean froze. As the water expanded into ice, it cracked the moon's outer crust. An alternative hypothesis connects the canyon's origin to the Odysseus impact, suggesting that the shock waves from the collision traveled around Tethys, generating a powerful resonance that ultimately fractured the crust and formed the fissure. Far beyond the main rings, at a distance of about 1.2 million kilometers from Saturn, orbits its largest moon, Titan. Located roughly 10 astronomical units from the Sun, it lies well outside our star's habitable zone and completes a nearly circular orbit around the gas giant in just under 16 Earth days. Titan surpasses Mercury in size by 5.6%, boasting a diameter of 5,152 kilometers. However, its mass, estimated at 5.68 times 10 to the 23rd kilograms, is merely 40% of Mercury's. This disparity leads to an average density of just 1.88 grams per cubic centimeter, about 1/3 of Earth's, which strongly suggests a fundamentally different chemical makeup. Current scientific models propose that Titan's interior is built around a massive, dense core composed mainly of silicate compounds, spanning approximately 3,400 kilometers in diameter. This core is enveloped by a thick mantle of highly compressed ice, which in turn forms the bed for a deep, frigid liquid ocean that extends for hundreds of kilometers. This subterranean ocean remains liquid, despite the intense cold, because it is rich with dissolved ammonia, methane, and various caustic salts that significantly lower its freezing point. Covering this ocean is a formidable crust, roughly 100 kilometers thick, made of water ice and methane hydrate. The constant gravitational tug from nearby Saturn relentlessly deforms this crust, creating widespread fractures that give rise to enormous cryovolcanoes, which then eject ammonia and water onto the moon's surface. On Titan, methane performs a role remarkably similar to that of water vapor in Earth's climate system. The moon's average surface temperature lingers at a mere 94 Kelvin, or minus 179 degrees Celsius, just below the boiling point of methane. As a result, even minor temperature shifts cause hydrocarbon vapors to condense and fall as rain, sustaining the moon's vast seas, lakes, and rivers. Titan's atmosphere is overwhelmingly dominated by nitrogen, which accounts for about 98.4% of its volume, while methane constitutes the remaining 1.6%. The extreme cold keeps this gaseous envelope dense and close to the surface, generating an atmospheric pressure that is 1.5 times greater than what you would experience on Earth. An orange-yellow tholin haze, made of tiny droplets of liquid methane and dissolved organic compounds, perpetually shrouds most of Titan's surface beneath multiple cloud layers. This distinctive haze absorbs and scatters sunlight, creating a strange anti-greenhouse effect that has long complicated direct observation. Nevertheless, by using the infrared cameras on the orbital Cassini spacecraft, scientists successfully assembled a partial map of the moon's surface. Although this map is not as detailed as one might wish, it is sufficient to identify the landscape's most striking characteristics. The face of Saturn's largest moon is defined by sharply contrasting patches, with some areas appearing bright where they reflect light, and others dark where they absorb it. One of the most prominent reflective regions, known as Adiri, is situated just south of the equator. This is where you will find one of Titan's tallest mountains, Doom Mons, which rises approximately 1.5 kilometers above the surrounding plains. The mountain spans 60 kilometers across. Its summit is marked with craters, and its slopes show relatively recent traces of powerful flows, all evidence suggesting that Doom Mons might be an active cryovolcano. Northeast of the mountain lies Titan's deepest depression, Jezero Crater, a gigantic collapsed feature that stretches for about 30 kilometers, with its floor situated nearly 2 kilometers below the adjacent plains. Jezero Crater is thought to be the vent of a colossal cryovolcano, forming a single, unified tectonic structure with the nearby Doom Mons. Stretching to the north of the mountain is the vast Mohini Fluctus, a wide area blanketed in material ejected from Doom Mons. This region extends for about 180 kilometers, broadening from 15 kilometers in the south to 60 kilometers in the north, where the flows of frozen material merge into expansive fields of sand dunes, composed of frozen methane and water ice. Our flight path now carries us over the dark territory of Fensal. Located in its northwestern sector is Titan's largest impact crater, Minerva, which has a diameter of 440 kilometers, making it about 3 times larger than any other crater on the Moon. The depression itself is only about 200 meters deep, and the encircling mountain ring does not exceed a height of 500 meters. Research indicates that Minerva is not only the largest, but also the oldest surviving crater on Titan, with an age estimated to be between 3 and 5 billion years, 100 million and 1.2 billion years. It has been heavily scarred by erosion and tectonic forces, and only its sheer immensity allows it to remain visible today. Minerva displays a well-defined internal structure. A small, flat plain sits at its center, surrounded by a ring of hills. This central zone, about 200 kilometers in diameter, has a light coloration that is easily seen from space. It is enclosed by a so-called moat, a 50-kilometer wide band of dark plains, which is then bordered by a ring of low mountains that form the crater's outer edge. Our next destination is to the south, where one of Titan's most impressive and enigmatic landforms, the Haute Arcus, is situated. A unique feature within the solar system, this is a bright arc-shaped region that stretches for roughly 600 kilometers. Radar data from Cassini suggests that Haute Arcus acts as a natural boundary between Rocky Mountains to its southeast and a wide valley. It is particularly noteworthy that certain areas within this region periodically change color, a phenomenon that is thought to be connected to cryovolcanic eruptions. The prevailing theory suggests these eruptions lay down a thin film of material on the surface, which then either flows into the nearest valley or simply evaporates into the atmosphere. From orbit, you can see brilliant channels that look like riverbeds carving their way down from the mountains toward the northwest. This path leads to a region called Xanadu, a vast lowland characterized by its extremely rugged landscape. The northwestern edge of Xanadu is defined by the Mithrim Montes, a set of 3 parallel mountain ranges spanning about 150 kilometers in length and averaging 1.9 kilometers in height. Nestled among the peaks of the southernmost range is Titan's highest point, which stands at an elevation of 3,337 meters. If you were to stand atop that summit and gaze westward, your view would be dominated by an immense, dark plain that extends for several hundred kilometers. This area, known as Shangri-La, is thought to have been a sea of liquid methane in the distant past. It's possible that this methane still exists beneath the ground, much like groundwater on Earth. While most of Shangri-La sits below Titan's average elevation and is quite flat, you can spot lighter-colored highlands that may have once been islands in a vast hydrocarbon ocean. West of Shangri-La is the bright, elevated region of Adiri. To its east, right near the border, lies the historic Huygens landing site. This spot marks the only time a human-made craft has ever touched down on a celestial body in the outer solar system. The Huygens probe was a key component of the Cassini-Huygens scientific mission, which departed from Earth in 1997. After a 7-year voyage, the spacecraft entered Saturn's orbit in 2004. In early 2005, the Huygens probe separated and began its descent into Titan's atmosphere, commencing a new era of discovery. Its companion, the Cassini orbiter, remained in orbit around the gas giant, both to conduct its own research and to act as a crucial communications relay for the probe. For nearly 2.5 hours, Huygens plunged through the atmosphere, its velocity carefully managed by a sophisticated parachute system, until it reached a surface impact speed of just 4.4 meters per second. The probe not only survived the instantaneous 15G shock of landing, but also began its scientific operations almost immediately. Huygens was outfitted with a comprehensive array of instruments, primarily focused on studying the dense atmosphere. These tools measured wind speed and direction, atmospheric composition, temperature, and electrical conductivity. The craft also captured images and sound recordings, and upon landing, it began to analyze the properties and makeup of the surface material. The initial photographs sent back from the surface showed a flat plane covered with rounded stones of varying sizes. Their smooth, eroded shapes provided clear evidence of being tumbled by powerful liquid currents long ago. A soil investigation was also carried out, using a special drill that penetrated 15 centimeters into the ground, while sensors measured the soil's density, composition, and structure. The analysis revealed a thin layer of small, round pebbles resting on a soft yet dense material with a consistency like wet sand or clay. As the drill bored into the ground, it released a plume of gaseous methane. This discovery strongly suggested that the soil at the landing site was akin to sand on an earthly seabed, thoroughly saturated with liquid hydrocarbons. In total, the probe successfully transmitted approximately 500 megabytes of information back to Earth, a collection that included 350 photographs. Subsequent, more detailed analysis of this data brought several extraordinary features to light. One such anomaly is a layer of near-total calm existing at an altitude of about 80 kilometers, which appears to split Titan's atmosphere into two distinct sections. This tranquil zone is impervious to both the high-altitude air currents and the surface-level winds, and the reason for its existence is still a mystery. Another of Titan's unique characteristics is the presence of two separate ionospheres, a feature not seen elsewhere in our solar system. The upper ionosphere is found at an altitude of roughly 1,200 kilometers and is a region of high electrical conductivity with a dense concentration of ionized particles, created by the solar wind and cosmic rays. A second, more perplexing ionosphere exists much lower, at just 60 kilometers above the surface. The mechanism behind the formation of this lower layer remains a topic of active scientific debate and investigation. Traveling northwest from the Adiri region brings you to Kraken Mare, Titan's largest sea of liquid hydrocarbons. It covers an area of about 400,000 square kilometers, making it just slightly smaller than Earth's Black Sea. The liquid in this sea is a highly viscous mixture, which has so far prevented precise depth measurements, though it is known to be over 100 meters deep in most areas. Further north, situated near Titan's pole, is another major basin named Ligeia Mare. With a diameter of 500 kilometers and an area of around 100,000 square kilometers, it ranks as the second largest sea on the Moon. These hydrocarbon seas are interconnected by a long, narrow channel called Ravazza, a strait that runs for 173 kilometers. The polar regions are also dotted with many smaller lakes and lagoons, all filled with liquid methane. In 2014, while reviewing images previously captured by the Cassini spacecraft, scientists noticed a large, bright feature that had appeared on the surface of Ligeia Mare. By comparing photos taken at different times, they observed that this object grew to a diameter of 260 kilometers over several months. Then, just as mysteriously as it appeared, the feature vanished almost instantly, leaving no trace behind. Several theories have been put forward to account for this strange event, which was nicknamed the Magic Island. The leading hypothesis suggests that temperature changes cause a constant churning of the liquid hydrocarbon layers within Ligeia Mare. This mixing process can release nitrogen bubbles from the sea's depths, which then rise to the surface and accumulate into vast, shimmering patches of foam. Because of the high viscosity of the hydrocarbons, these bubbles can expand to diameters of up to 400 meters and persist for months at a time. When viewed from orbit, their strong reflection of infrared radiation makes them look like vast islands. These formations would have presented a major obstacle for a submersible probe mission that was originally scheduled for launch in 2010, but that project has since been delayed indefinitely for a variety of reasons. Instead, precedence was granted to the Dragonfly program, which is now being developed by the National Aeronautics and Space Administration, or NASA. This spacecraft, presently in its design stage, recently succeeded in crucial rotor blade trials. Dragonfly is conceived as an octocopter, a craft propelled by 4 sets of rotors that can maintain flight even with the loss of multiple blades. In a departure from the earlier Ingenuity Mars helicopter, Dragonfly will be powered by a radioisotope thermoelectric generator. This power source will permit the vehicle to reach altitudes as high as 4 kilometers and achieve speeds approaching 36 kilometers per hour. The probe's scientific instruments are just as remarkable. It will carry a multifaceted camera designed to capture sweeping panoramic vistas of the landscape, as well as detailed close-up images of the soil. Additionally, a mass spectrometer will enable it to analyze the chemical makeup of atmospheric samples and reveal the internal composition of rocks. Information gathered by Dragonfly may finally shed light on a pivotal question: whether there is any prospect of finding even the most basic forms of life. The potential for life on Titan is still a topic of vigorous scientific discussion. The arguments against it are compelling, as the frigid surface temperatures, the existence of poisonous hydrogen cyanide in the air, and the lack of liquid water seem to preclude biological organisms familiar to us. Conversely, Titan exhibits an astonishing variety of organic molecules. Its surface provides conditions where nitrogenous bases and amino acids, which are the fundamental components of proteins, RNA, and DNA, can form spontaneously. It is also understood that liquid methane could serve as a solvent, possibly taking the place of water in biochemical processes. Moreover, laboratory experiments have demonstrated that a combination of liquid hydrocarbons and phosphine, under Titan-like conditions, creates a medium reminiscent of primordial Earth's chemical soup, suggesting that entirely alien life forms could exist there. Over 400 years ago, in the year 1610, Galileo Galilei achieved one of the most significant astronomical breakthroughs of his era. Using a telescope that would be considered simple by today's standards, he spotted 4 bodies orbiting near Jupiter. The first, named Ganymede, is now recognized as the largest moon in our solar system. 2 of the others, Europa, and Callisto, are now viewed as prime locations to search for life beyond Earth. The final moon, positioned nearest to the gas giant, was given the name Io. For an extended period, the limits of technology made it impossible for scientists to make out fine details on this moon's surface, leaving its makeup and internal arrangement a matter of conjecture. Yet, with scientific progress, astronomers steadily compiled more data. We now know that Io ranks among the solar system's largest moons, with only Ganymede, Titan, and Callisto being larger. It has a radius of 1,821 kilometers and a mass of roughly 8.9 times 10 to the 22nd power kilograms. While Io is almost the same size as Earth's moon, a comparison of their masses reveals Io to be 21% heavier, which points to Io having the highest average density of any moon in the solar system. Its density is calculated to be approximately 3.5 grams per cubic centimeter, a value considerably greater than that of most nonmetallic rocks. Unraveling the cause of Io's unusual density requires an examination of its deep interior. Current models of celestial structures suggest that Io possesses a fairly dense core made of iron and sulfur. This core accounts for about 20% of the moon's total mass and is estimated to have a radius between 350 and 900 kilometers. With these specifications, theoretical calculations indicate that internal heat production would not be enough to liquefy the majority of the core, a finding that is corroborated by Io's absence of an intrinsic magnetic field. Mathematical models suggest this core is enveloped by a mantle made up of at least 75% forsterite, a mineral rich in magnesium. It is estimated that the mantle's outer portion is molten, reaching temperatures above 1,200 degrees Celsius. In contrast, the immense pressure keeps the deeper layers solid despite the intense heat. This entire mantle is encased in a lithosphere that varies in thickness from 12 to 40 kilometers. While this crust is a solid shell in most places, it fractures in certain areas, creating vast rifts that fill with molten rock. Spectrographic analysis reveals that Io is nearly devoid of water, ice, or frozen gases, setting it apart from the majority of other moons. Its external surface consists mainly of basalt and sulfur, mixed with other dense minerals, which accounts for its unusually high density. By the start of the 21st century, the surface of Io had been investigated by no fewer than 5 robotic orbital probes. The largest volume of critical information, however, was gathered during the Pioneer and Voyager missions of the 1970s. These observations showed that Io's landscape is marked by fresh, solidified lava flows and ancient volcanoes that erupted millennia ago, with some of these volcanic events dwarfing those seen on our own planet. In all, approximately 400 active volcanoes have been identified on the moon's surface, which is about 2.5 times less than the number found on Earth. Although Io's surface area is considerably less than Earth's, it holds the title of the most volcanically active body in our solar system. It's hardly surprising that such a remarkable world has captured the intense focus of astronomers. Through various research missions, an enormous collection of photographs at different resolutions was amassed, enabling the creation of a comprehensive geological map of Io in 2012. The high quality of this map makes it possible to study the moon's largest geological features, including its plains, mountain ranges, vast lava flows, and countless volcanoes. Among the most stunning sights is an immense orange-brown ring situated in the moon's southeastern hemisphere. This enormous feature spans more than 1,000 kilometers, making it comparable in size to a large country in Africa. It is theorized that this ring was formed by sulfur deposits ejected from the ancient Pele volcano, which sits at its very center. Photographic analysis in both infrared and visible light reveals the volcano's patera, a multi-tiered depression 20 kilometers across, filled with lava. The surface temperature of this molten rock is uneven and constantly in flux, with the hottest areas reaching an incredible 1,300 degrees Celsius. The patera is thought to be linked by an underground channel directly to the moon's superheated mantle. Volatile substances dissolved in the lava constantly try to rise, churning the molten rock within the fissure. This process causes the thin solidified crust on the lava lake's surface to regularly crack and shatter, unleashing powerful splashes and fiery eruptions. Some of these eruptions are capable of launching solidified sulfur particles to heights exceeding 1,000 kilometers, sending them directly into space. As these volcanic deposits lose momentum to gravity, they spread out across the moon's surface before gently settling, which is how the colossal ring visible from orbit was formed. While many of Io's volcanoes produce similar features, the ring around Pele is by far the largest. This relentless volcanism is the primary driver behind the formation of Io's distinctive atmosphere. Based on available information, the moon's gaseous shell is incredibly thin and is composed mostly of sulfur dioxide. The density of this atmosphere fluctuates dramatically depending on the location. Within volcanic plumes, for instance, the gas pressure is 25 million times lower than it is far from an eruption. The atmospheric pressure on Io's sunlit side is, on average, 1 billion times lower than Earth's standard pressure, while the night side exists in a near-total vacuum, with an atmospheric density trillions of times lower than our own. Yet despite this extremely tenuous atmosphere, auroras have been detected on Io. These colorful glows are created when charged cosmic particles, accelerated within Jupiter's powerful magnetosphere, slam into the nearby moon's atmosphere. In a departure from what we see on Earth, Io's auroras typically appear at its equator. This is because particles traveling along a tangential path must pass through the densest section of the atmosphere there. As our journey across Io takes us in a northwesterly direction, we leave the sedimentary ring of Pele behind, and soon arrive at the immense Montes mountain range. This entire range measures about 540 kilometers in diameter. Among its peaks, South Mons is particularly notable, with a base that is 145 by 155 kilometers. This particular mountain soars more than 18 kilometers above the moon's average surface level, making it twice the height of Mount Everest. The highland's total area is nearly 18,000 square kilometers, which is comparable to the size of a small European nation like Montenegro or Slovenia. Both the appearance and structure of this landform point to its creation in a monumental tectonic disaster. It is likely that in the distant past, a large piece of Io's developing lithosphere tilted and was partially driven down into the mantle, leaving one of its edges permanently raised above the surface. This event created a sheer cliff on the mountain's southeastern slope that is roughly 15 kilometers high, classifying it as one of the tallest escarpments found anywhere in the solar system. Such a feature is unique because it couldn't form under Earth's stronger gravity, and other worlds lack the necessary tectonic activity. If you continue with us on this northwesterly path, you will soon come upon a gigantic chasm called Loki Patera. This feature is the largest volcanic depression on Io, boasting a diameter of 200 kilometers and a total area exceeding 500,000 square kilometers. To put that in perspective, this single depression is about 1.5 times larger than Lake Baikal, one of the most magnificent lakes on our planet. However, in place of water, this abyss is filled with scorching, sulfurous silicate lava. Several kilometers beneath the surface, this immense lava lake maintains a direct connection to the mantle, which provides a seemingly endless supply of molten material to replenish it. During its calmer phases, the surface temperature of Loki Patera fluctuates between 270 and 313 Kelvin, which is equivalent to -3 to 40 degrees Celsius. This relatively cool temperature is the result of the uppermost lava layers losing heat to Io's rarefied atmosphere, which causes them to slowly solidify into a growing solid crust. Over a period of 400 to 600 days, this crust accumulates a critical mass until it eventually fractures under its own weight. As it sinks, it sets off waves of fresh lava that flood the surface, spreading out at a steady rate of 1 kilometer per day and starting the cycle anew. Eventually, the lava lake settles, and a solidifying rigid crust begins to form over its surface once again, lasting only until the start of the next flooding cycle. This celestial body is widely considered hostile to the formation of life, given the near-total absence of water and carbon dioxide on its surface, both of which are fundamental for life as we understand it. However, it's hypothetically possible that the conditions within Loki Patera and other similar lava lakes could support the emergence of unconventional life forms. Such organisms would have to be resilient to extreme heat and capable of harnessing energy from chemical reactions involving sulfur or iron. Life forms with similar characteristics do exist on Earth, typically found near the vents of underwater volcanoes or in secluded oceanic caves, but the likelihood of this on Io is quite low due to its intense tectonic activity and dramatic temperature swings. It is important to remember that while the highlands and volcanoes are Io's most dramatic features, they cover a surprisingly small portion of its terrain. The vast majority of the tectonically active areas are made up of comparatively flat plains, which are blanketed in a deep layer of sulfur deposits. When observed from space, these expanses are easily identified by their lighter coloring, with the most massive among them stretching for thousands of kilometers. For instance, if you were to travel west from Loki Patera, moving past a landscape dotted with numerous small volcanoes and lava flows, you would arrive at Medusa Fossa. This is a vast, light-hued region with a relatively smooth, irregular shape, encircled by mountains and large volcanic craters known as Patera. Its diameter is estimated at roughly 2,600 kilometers, and its surface area accounts for about 12.6% of the entire Moon. Most of this area is consistently flat, though in certain places the plain is dissected by lava flows originating from nearby volcanoes. One theory suggests that the lithosphere is thicker beneath Medusae Fossae, creating a structure akin to Earth's continents, which explains why such a large segment of the surface remains stable for extended periods. An alternative hypothesis proposes that the upper mantle layers on Io are only partly molten, with no liquid magma existing directly under the tectonic planes. Observations confirm that, in stark contrast to the volcanic regions, Io's plains experience a frigid climate. The temperature in the Medusae Fossae area is around 110 Kelvin, or minus 163 degrees Celsius, which is only slightly different from the Moon's average, but hundreds of degrees colder than in most volcanic pateri. At this temperature, Sulfur dioxide from volcanic emissions freezes and settles onto the surface as frost, crafting a smooth, rolling landscape painted in countless shades of yellow, red, and black. Navigating the gentle sulfur-caked hills of Medusae Fossae and heading northwest, we would find another major feature, a large depression called Amirani. Like the majority of Io's volcanoes, Amirani is essentially a fissure in the moon's crust filled with molten rock, and its diameter at the widest point measures only 37 kilometers. Despite this, when seen from space, the volcano is nearly as prominent as the moon's largest landmarks. This visibility is due to the several gigantic flows of solidified lava that surround Amirani, which create a stark, dark contrast against the pale adjacent plains. The most massive of these flows extends northward for over 300 kilometers and is up to 200 kilometers wide, making this formation the largest active lava flow in the entire solar system. The second largest flow stretches west for approximately 250 kilometers, while once thought to be a separate feature, detailed imagery has since confirmed it is also part of Amirani. Amirani itself possesses a complex internal structure, and it is thought that additional magma chambers exist beneath the surface in this area, separate from the primary active zone. Eruptions from these secondary chambers periodically fuel volcanic activity beyond the main depression. Infrared scans show that the main patera is heated to about 1,900 Kelvin, or 1,630 degrees Celsius, while surrounding hotspots blaze at 1,200 Kelvin, or 930 degrees Celsius. This intense heat is likely caused by a rising plume of magma from deep within the mantle, continuously feeding molten material to the volcano. The available data also indicates that Amirani is probably a very young shield volcano, which, over geologic time, will build up an expansive, flat shield several hundred kilometers in diameter. It is quite possible that this volcano will one day grow to resemble Olympus Mons on Mars. It's undeniable that for a body of its modest size, Io displays an exceptionally high level of tectonic activity. Because of its low mass, it lacks the significant reserves of radioactive materials whose decay provides the internal heat for most planets. Instead, the extraordinary activity of this celestial body is attributed to the powerful tidal forces exerted by Jupiter, which, combined with an orbital resonance that locks Io in a stable path, dramatically heats its interior and deforms its crust. When these titanic eruptions are combined with Io's low gravity, the results are truly spectacular. Colossal plumes of material are blasted into space, sustaining a diffuse cloud of particles that envelops the moon. Some of this debris rains back down onto Io, while other particles are captured and accelerated by Jupiter's magnetic field, ultimately bombarding the gas giant's sphere, settling on its other moons or contributing to its rings. It is precisely these kinds of magnificent eruptions that are a constant feature in the region known as Tvashtar Patare, situated in Io's northern hemisphere. You're looking at an area of intense volcanic activity, spanning a diameter of roughly 300 kilometers. Current information suggests the presence of multiple volcanic craters, known as paterae, which are all likely fed by a common subterranean magma reservoir. For instance, between 1999 and 2000, eruptions launched material to an altitude of 385 kilometers, blanketing a region over 700 kilometers in radius with volcanic fallout, while immense flows of sulfurous silicate lava inundated the surrounding landscape. Then, in 2006, another significant eruption commenced from the very same spot, continuing for 530 days, which made it the longest-duration volcanic event ever witnessed on Io. On this occasion, the plume of ejecta soared to a height of 330 kilometers, expelling thousands of tons of matter into the void. It's evident that Tvashtar is an exceptionally active tectonic zone, and by analyzing its volcanic emissions, we can gather invaluable information about the internal makeup and structure of this moon. To call Io a uniquely captivating celestial object whose exploration is far from complete would be no overstatement. Specifically, on February 3, 2024, the Juno space probe executed a close flyby, passing just 1,500 kilometers above the moon's surface and sending back a large number of high-resolution images. These photographs reveal enormous cracks in the lunar crust, alongside active volcanic plumes and extensive lava flows, and the hope is that subsequent flybys will allow for a spectral analysis of its atmosphere to better define its composition. However, despite the significant interest from astronomers in this world, there are no dedicated missions scheduled to investigate it at present. Missions like the Jupiter Icy Moons Explorer, or JUICE, and Europa Clipper are instead concentrating on Ganymede, Europa, and Callisto, primarily because of their potential to harbor life. And while NASA did announce a proposed mission named the Io Volcano Observer in the early 2020s, designed to study Io's volcanoes, it has so far remained on the drawing board for a variety of reasons. Positioned at an average distance of about 40 astronomical units from the Sun, Pluto is a profoundly remote and dim celestial body. It traces a highly elliptical path around the heart of our solar system, taking 248 Earth years to complete a single orbit. Thanks to extensive calculations, we have determined its radius to be 1,188 kilometers, which makes it considerably smaller than any planet, and even some moons, including our own. By observing its distinct movement, scientists have accurately calculated Pluto's mass to be a mere 13 times 10 to the 21st power kilograms, which is just 18% of the mass of Earth's moon. You can readily see how its properties align it more with smaller celestial objects like Eris, Ceres, or Sedna. It was precisely for this reason that, back in 2006, its classification was officially changed to that of a dwarf planet. The drawn-out and elliptical nature of Pluto's path creates a very lengthy orbital period. For the first time since it was discovered, the dwarf planet reached its closest point to the Sun, or perihelion, in 1989, at a distance of 29.7 astronomical units. From that point onward, its distance from the Sun has been steadily growing, and by the year 2087, it will approach its farthest point, or aphelion, at 49.3 astronomical units. Consequently, Pluto remains an incredibly remote and faint object, invisible to the unaided eye from Earth, and appearing only as a hazy, brownish circle, lacking any discernible features, even in powerful telescopic images. To overcome this challenge, the New Horizons automated space probe was dispatched toward Pluto in 2006. It embarked on a 9.5-year journey, during which it also captured detailed pictures of Jupiter, before finally arriving at its primary destination in 2015. During its flyby, the probe executed around 400 distinct observations and gathered over 6 gigabytes of data, a massive collection of information that required more than a year to transmit back to Earth. Regrettably, the mission's specific trajectory meant that a complete photographic map of the dwarf planet's surface could not be created, as New Horizons was designed to fly past Pluto and continue on to investigate more distant objects, rather than entering into its orbit. Before we explore the specifics of Pluto's terrain, it's essential for you to understand its internal structure. According to the most widely accepted model, Pluto has a massive core with a diameter of approximately 1,700 kilometers, composed of a combination of various water ices and rocky materials. This core is then surrounded by a kilometer-thick icy mantle, which may be a site of weakly understood tectonic processes. This mantle, in turn, is concealed by a crust consisting of a blend of crystals that formed deep within the dwarf planet. It's believed that beneath this crust, there is a very salty and caustic ocean containing a large quantity of dissolved ammonia. In stark contrast, the surface temperature of Pluto is exceedingly low, never exceeding 6 Kelvin, or minus 213 degrees Celsius. Our tour across Pluto's surface begins with its most famous and well-documented feature, Tombaugh Regio. This immense territory is situated in the equatorial zone of the dwarf planet and has a shape that strongly resembles a stylized heart, giving rise to its popular, unofficial name, the Heart of Pluto. The feature itself stretches for 2,300 kilometers, meaning this single plane covers approximately 1/4 of the entire surface area of the celestial body. Tombaugh Regio presents a varied surface. If you look at its western section, you will find the much smoother and brighter expanse known as Sputnik Planitia, which measures 1,192 kilometers across. An elevation map reveals this area to be a vast basin filled with a deep blanket of frozen nitrogen, carbon monoxide, and methane. These compounds give the region its pale hue, which bounces back 90% of the sunlight it receives, and the near total absence of impact craters suggests it is geologically very young. The leading theory proposes that Sputnik Planitia was created approximately 100 million years ago following Pluto's impact with a massive object. This event carved out an enormous crater that subsequently filled with water from the dwarf planet's subsurface ocean. You can see supporting evidence in the plane's distinct topography, which features many smooth segments, between 20 and 30 kilometers wide, broken up by hills and troughs. This pattern looks a lot like convection cells that form in heated liquids, offering what could be indirect proof of a warm interior beneath Pluto's surface. You'll find that Tombaugh Regio is framed by quite tall mountain ranges. To the west of Sputnik Planitia, for instance, are the Hillary Montes, which ascend to heights of 3 kilometers. Meanwhile, in the southern portion of this heart-shaped feature, the Tenzing Montes tower even higher, with some peaks surpassing 6 kilometers above the average surface elevation, establishing this as Pluto's loftiest mountain range. Remarkably, these towering cliffs are probably composed mostly of water ice, which turns rock hard in such extreme cold. If you venture a bit more to the south, you will encounter a deep basin encircled by colossal stratified ridges of ice and rock, along with a great deal of solidified material ejected from impacts. The chemical makeup of these features holds immense scientific value, as analyzing it could offer clues about Pluto's internal composition. Moving on, the eastern section of Tombaugh Regio has a distinctly darker appearance and is heavily pockmarked with craters, a clear sign that it is considerably more ancient than Sputnik Planitia. As you continue eastward along the equator, a series of dark patches, each hundreds of kilometers across, becomes visible. Known as maculae, these features are named for shadowy figures from different mythologies. For instance, one of them is called Balrog. These patches collectively create an immense feature called Cthulhu Macula, which wraps around Pluto's equatorial belt. Tall mountain ranges divide these maculae, and their surfaces are scarred by deep canyons that stretch for hundreds of kilometers. Cthulhu Macula, Pluto's most extensive dark area, extends for nearly 3,000 kilometers and reflects a mere 30% or less of the light it receives. In stark contrast to the brilliant Sputnik Planitia, the true nature of these maculae remains uncertain. Scientists theorize their dark tone comes from a high concentration of complex organic molecules called tholins, which, alongside the dense cratering, points to a very old age. You should also know that the surface of Cthulhu Macula is varied. Its western end is hilly, the middle section is a flat plain, and the eastern portion is a landscape of mountains and craters. Now, if we move on from the shadowy expanse of Cthulhu Macula and travel northward, you will discover the vast Lowell Regio, an enormous plain that encircles Pluto's North Pole. Curiously, this region is presently the most brightly lit portion of the dwarf planet's surface. This is because Pluto's rotational axis is tilted at a severe angle to its orbital plane, causing its north pole to be aimed directly at the Sun during this phase of its journey. Many researchers think this explains why Pluto's atmosphere has thickened threefold in the last 30 years, even as it moves farther from the Sun. Sunlight is likely vaporizing polar nitrogen ice, which then supplements the planetoid's gaseous shell. When you examine Pluto's path through space, you'll see it has a few peculiarities that set it apart from the major planets of our solar system. Its orbit is not only markedly inclined relative to the ecliptic plane, but the dwarf planet also experiences a continuous cyclical wobble around a specific point. This motion is caused by the gravitational pull of a very large moon named Charon, which possesses a mass of 1.52 times 10 to the power of 2 21st power kilograms, over 11% of Pluto's own mass. Consequently, Pluto and Charon orbit a shared center of gravity, which lies in the space separating them. They are also tidally locked, meaning they perpetually show the same face to one another. You will notice that Charon's surface is considerably dimmer than Pluto's, and displays significant amounts of water ice only in specific areas, where it is blended with frozen methane and nitrogen. Besides Charon, you'll find several other satellites, though they are all considerably smaller and have non-spherical shapes. Nix and Hydra, which were first spotted in 2005, measure several tens of kilometers across. The more recently found moons, Kerberos and Styx, are even smaller, with diameters no greater than 10 kilometers. It is thought that all these bodies are composed primarily of water ice, and were probably ensnared by Pluto's gravitational field from the Kuiper belt. It's a shame that the cameras aboard the New Horizons spacecraft were unable to capture a large part of Charon's surface. Nevertheless, on the portion of the moon that you can see, a number of fascinating geological formations are apparent. For instance, just south of its equator lies a widespread area that has been named Vulcan Planum. Although its precise area is still undetermined, Charon spans at least 400,000 square kilometers, a size comparable to a mid-sized European nation. This is where you will find its tallest mountain, Kubrick Mons, which boasts a diameter of roughly 40 kilometers and an estimated height of 4,000 meters. A vast ring-like depression, in some places plunging to a depth of 2 kilometers, encircles this prominent peak. There is speculation that Kubrick Mons could be a cryovolcano, a volcano that erupts volatile materials instead of molten rock. If this theory holds true, the surrounding terrain might have collapsed under its own mass after the depletion of a subterranean reservoir. To the north of Vulcan Planum, you encounter the vast expanse of Oz Terra, a landscape heavily scarred by countless impact craters. Separating Oz Terra from Vulcan Planum is a network of colossal escarpments and fissures, creating a total vertical drop of about 1 kilometer. The most immense of these features is Serenity Chasma, a canyon that stretches for 200 kilometers in length, measures between 40 and 50 kilometers in width, and can reach a staggering depth of 7 kilometers. Unfortunately, the steep walls cast such a deep shadow that studying the chasm's floor proves exceptionally challenging. Even farther north, approaching the pole, lies the enormous Mordor Macula, a feature measuring 475 kilometers across. Its origins are still a topic of scientific discussion, but the leading hypothesis suggests that nitrogen and methane escape Pluto's atmosphere, are captured by Charon's gravity, and then freeze onto its poles. Over time, exposure to ultraviolet radiation converts these compounds into tholins, which steadily darkens the surface of this celestial body. This entire hypothesis, however, awaits confirmation from future missions. Charon remains a world of profound mystery for us, as our exploration of it has barely begun. The Pluto-Charon system is undeniably one of the most fascinating arrangements in our solar system, yet it remains significantly under-examined. As the New Horizons spacecraft has already departed its vicinity, these worlds are now receding from us, taking their secrets along with them. At present, the research probe is more than 50 astronomical units from Earth, continuing to transmit infrequent yet invaluable data back to us. By approximately the year 2030, its power systems will finally be depleted, leaving the spacecraft to drift in complete silence through the cold, empty expanse of space. On April 15, 2021, the New Horizons Automated Station joined an exclusive club, becoming the 5th human-made object to surpass the 50 astronomical unit mark from the Sun. This symbolic threshold had previously been crossed only by the Voyager 1 and 2 probes, along with the Pioneer 10 and Pioneer 11 research craft. It is almost certain that none of these cosmic travelers will ever return to their home world. While some continue to carry out their missions, others have long ago ceased communication, falling silent forever. The New Horizons spacecraft began its mission on January 19, 2006, and is now at a distance of 52 astronomical units, speeding away from Earth at 14 kilometers per second, or about 3 astronomical units per year. Its primary objective was to study Pluto and Charon, a mission it completed successfully, and it remains operational to this day. Like many other interplanetary stations, New Horizons executed a gravity assist maneuver around Jupiter before proceeding to its main destination. This flyby not only gave the spacecraft a significant speed boost, but also yielded high-resolution images of the solar system's largest planet and its satellites. In fact, the probe's cameras captured the first-ever video footage of a volcanic eruption on Io, one of Jupiter's moons. Having received this crucial acceleration, the spacecraft set a course for its primary target, Pluto. The mission's core objective was an in-depth study of both Pluto and Charon, which involved photographing and mapping the surfaces of these remote objects. The probe also gathered data on their magnetic fields, solar wind interactions, atmospheric compositions, and surface reflectivity, all while searching for any undiscovered moons and refining Pluto's orbital path. Even after fulfilling its main purpose, the research probe's utility did not end. Its trajectory carried it beyond Pluto's orbit to investigate objects within the Kuiper Belt, resulting in images of bodies such as Quaoar and Arakoth. Furthermore, the spacecraft's cameras were used to measure the distances to the stars Proxima Centauri and Wolf 359 through parallax. Unfortunately, starting in the year 2026, the onboard power source will start to fail, forcing the progressive shutdown of the station's systems. New Horizons will continue its voyage out of the solar system, and by 2038, it will be 100 astronomical units from the Sun. At that point, its power supply will completely cease to function, making any further communication impossible, and the craft will follow a hyperbolic orbit away from our system, never to return. A similar destiny was met long ago by two other interplanetary probes, the Pioneer 10 and Pioneer 11 scientific stations, which humanity dispatched into interstellar space. Pioneer 10 began its mission on March 3, 1972, and is now 127 astronomical units from Earth, traveling at approximately 12 kilometers per second, or 2.5 astronomical units annually. Its main assignment, a study of Jupiter, was successfully achieved, though the craft is now non-operational. After a journey of 641 days, the Pioneer 10 spacecraft arrived in the Jupiter system on December 4, 1973. During its flyby, it captured photographs of the gas giant's surface and its largest moons, while also taking measurements of the planet's atmospheric composition and powerful magnetic field. A significant finding revealed that Jupiter radiates 2.5 times more thermal energy than it absorbs from the Sun. This groundbreaking data provided the foundational knowledge for comprehending the structure of gas giants and their satellites. Its sibling craft, Pioneer 11, continued this exploration with a flyby of Saturn, where its instruments gathered vital information on the planet's magnetic field, and its cameras captured an extensive collection of images detailing the gas giant, its iconic rings, and its moons, Titan and Mimas. After fulfilling their primary objectives, both Pioneer probes embarked on an extended voyage, venturing ever deeper into space, and are now estimated to be about 100 astronomical units from our Sun. Communication, however, was eventually lost. Pioneer 10 sent its final transmission in 2003, while its counterpart fell silent back in 1995. It is now presumed that these pioneering craft are swiftly making their way beyond the bounds of our solar system. Let's now consider the Voyager 1 spacecraft, which launched on September 5, 1977. It is currently 154 astronomical units from Earth, and is receding at a speed of roughly 17 kilometers per second, or 3.6 astronomical units per year. Although its main mission to study Jupiter and Saturn was completed with great success, the probe now functions with limited operational capabilities. The scientific contributions of Voyager 1 are immeasurable, as it led to the discovery of several of Jupiter's moons and a previously unknown ring system. Its cameras documented active volcanoes on the moon Io and definitively proved that the Great Red Spot is a colossal storm. After sending back hundreds of detailed images of our solar system's largest planet and its moons, the probe crossed Neptune's orbit and transmitted a wealth of valuable data regarding interstellar plasma. Having long since passed the Kuiper Belt and the heliopause, Voyager 1 is now rapidly traversing the scattered disk region as it heads toward the inner boundary of the Oort cloud. It holds the dual distinction of being both the most distant human-made object from Earth and the fastest artificial craft exiting our system. As the first probe to travel so far out, Voyager 1 has given scientists a unique opportunity to study the heliopause, the cosmic boundary where the solar wind is counterbalanced by the pressure of interstellar gas, creating complex structures of particles and magnetic fields essential to understanding universal processes. Unfortunately, around the year 2025, the probe's radioisotope thermoelectric generator is projected to be depleted, at which point all contact will be permanently lost. According to calculations, Voyager 1 will reach the inner edge of the theoretical Oort cloud in 300 years. It will then take an estimated 30,000 years to cross this vast region, after which it will finally depart the solar system. In another 10,000 years, the probe will pass within 1.6 light-years of the star Gliese 445, before it is lost forever in the depths of interstellar space. When discussing Voyager 1, it is essential to mention its mission counterpart, Voyager 2, which departed Earth on August 20, 1977. This second probe targeted Saturn, Uranus, and Neptune, but it first executed a close approach to Jupiter to gain a crucial gravitational assist. The resulting images revealed Jupiter's rings and the detailed surfaces of its moons, Europa and Ganymede, while its flyby of Saturn yielded data on the gas giant's temperature and magnetic field, along with the discovery of several previously unknown moons. The probe's trajectory past Uranus and Neptune provided photographs that led to the discovery of 17 new moons and the faint ring systems surrounding both ice giants. The gravitational pull of Neptune ultimately altered Voyager 2's path, sending it out of the ecliptic plane and thereby ending its tour of the planets. Its scientific usefulness, however, was far from over, as it went on to participate in measuring stellar distances and studying the heliosphere. At present, Voyager 2 is already 128 astronomical units away from the center of our system, a distance that increases by 1,537 kilometers every second. In about 42,000 years, it is projected to approach Ross 248, a faint red dwarf in the constellation Andromeda, passing it at a minimum distance of about 1.7 light-years. Looking much further ahead, in 100,000 years, the probe has a chance to fly past Sirius at a distance of 4.3 light-years, though detecting such a tiny object from Earth at that range would be impossible. For nearly a century, our planet has been broadcasting an immense volume of structured radio signals out into the cosmos. It's plausible that civilizations near stars like Arcturus, 37 light-years away, or Aldebaran, at a distance of 65 light-years, could one day receive these transmissions. Moreover, our world's signals might eventually be heard on the surface of any number of potentially habitable exoplanets, such as Ross 128b or Gliese 667cc. Nevertheless, the triple-star system of Alpha Centauri stands as the closest stellar neighbor to our Sun, making it the most logical destination for a future inaugural interstellar mission. It is well established that Alpha Centauri is a multiple system composed of 3 distinct stars. The 2 most substantial of these stars are situated in relative proximity and, to the unaided eye, blend into a single point of light. They revolve around a shared center of gravity in orbits that are slightly elongated, taking approximately 80 years to complete one full cycle. The separation between these 2 stars can extend to a maximum of 35 astronomical units, while at their closest approach, it shrinks to about 11.2 astronomical units. The distance separating our Sun from this pair is approximately 4.36 light-years. The system's largest, most massive, and most luminous member is Alpha Centauri A. This is a main sequence star with a mass about 8% larger than the Sun's and a radius that is roughly 1.22 times greater than our own stars. While its surface temperature and spectral type are comparable to the Sun's, Alpha Centauri A radiates 1.5 times more light energy. As of now, there are no confirmed exoplanets orbiting this star. However, back in 2021, infrared observations suggested the possible presence of a planet. Initial estimates place its mass somewhere between 9 and 35 times that of Earth, with a size ranging from 3.3 to 7 Earth radii. This theoretical world is believed to be positioned at a distance of 1.1 astronomical units from its host star, completing an orbit in a period similar to 1 Earth year. Of course, this information awaits confirmation through further observations, which could be undertaken by powerful instruments like the James Webb Space Telescope or various ground-based observatories. The system's second component is known as Alpha Centauri B, or Ptolemy. It too is a main sequence star, but it possesses about 10% less mass than the Sun and has a radius measuring approximately 0.86 times that of our star. In addition, this star is somewhat cooler than the Sun, boasting a surface temperature around 5,260 Kelvin, which is just below 5,000 degrees Celsius. This combination of traits gives the star a distinctly orange color, and its overall brightness is about half that of our Sun. Alpha Centauri B also emits a notably higher amount of energy in the X-ray spectrum compared to other stars of its type. It is an active star, with its surface frequently erupting in bright flares and ejections. Around this star, too, no confirmed exoplanets have been found. In 2012, a team of astronomers from the Geneva Observatory analyzed 4 years of the star's movement and proposed the existence of a very close planet. They suggested it had an orbital period of about 12 days and a radius slightly less than Earth's. However, a subsequent review 3 years later revealed a mathematical miscalculation in the data analysis, and the planet's existence was officially disproven. The third member of the system stands in stark contrast to its companions. This star is a red dwarf with a mass just 12% of the Sun's and a size about 7 times smaller. Its surface temperature barely surpasses 3,000 Kelvin, and its luminosity is an incredibly faint 0.1% of our stars. Of all the stars in the Alpha Centauri system, this celestial body is the nearest to the Sun, at a distance of 4.25 light-years. This proximity earned the star the name Proxima Centauri, which is Latin for the nearest. Interestingly, the distance to this object is steadily shrinking and is projected to close to just 3.11 light-years in 26,700 years. Despite this, its extreme dimness makes it completely invisible from Earth without a telescope. Proxima Centauri is positioned at a significant distance from the other 2 stars in its system, currently separated by about 13,000 astronomical units, or 0.21 light-years. Over the next 300,000 years, this gap is expected to narrow to 4,100 astronomical units. The red dwarf takes 547 years to complete a single orbit around the system's shared center of mass. In a departure from its larger neighbors, the Proxima Centauri system is home to 2 confirmed exoplanets and at least 1 other hypothetical object. Furthermore, infrared observations of the star hint at the potential presence of a dust ring and possibly numerous smaller bodies like asteroids or comets. The system's first planet, designated Proxima Centauri B, was identified in 2016 through the radial velocity method. Its existence was definitively confirmed 4 years later, in 2020, by spectroscopic analysis using the Very Large Telescope, the largest ground-based telescope on Earth. According to the updated findings, this exoplanet orbits its star at a distance of roughly 0.05 astronomical units, completing a full revolution in about 11 Earth days. Calculations indicate that its mass is 20% greater than Earth's, while its radius is about 1.3 times larger. Mathematical models suggest that Proxima Centauri b receives about 1.5 times less heat from its star than Earth gets from the Sun. Its average temperature is estimated at 234 Kelvin, or minus 39 degrees Celsius, which implies that under certain conditions, liquid water could exist on parts of the planet. However, due to its incredibly close orbit, the planet is almost certainly tidally locked, meaning one hemisphere perpetually faces its star. Under these conditions, a thick atmosphere might buffer the unavoidable shifts in temperature, yet Proxima Centauri, like countless other red dwarfs, is prone to frequent, powerful eruptions of stellar matter and blasts of ionizing radiation. It is widely believed that this stellar activity steadily erodes the atmospheres of any planets orbiting nearby. While a powerful magnetic field could shield a planet from this destructive force, the chances that Proxima Centauri b has one are exceedingly slim. Then, in 2020, the existence of a second planet within this system was confirmed. Known as Proxima Centauri c, this world orbits at a distance of roughly 1.5 astronomical units from the system's heart, and completes its circuit in just over 5 years. Its mass is estimated to be between 6 and 8 times that of Earth, although its radius remains undetermined, meaning this exoplanet could be classified as either a mini-Neptune or a super-Earth. Given its vast distance from the parent star, Proxima Centauri c is exceptionally cold, with a surface temperature of approximately 39 degrees Celsius Kelvin, which is equivalent to minus 234 degrees Celsius. Furthermore, some observations indicate the planet might possess a ring system with a radius measuring about 1/5 of Jupiter's. This finding adds another layer of intrigue to this distant and frozen world. An analysis of the most recent information from the Very Large Telescope points to the possible existence of a tiny exoplanet with a mass about 0.25 times that of Earth. This potential world would be situated only about 0.029 astronomical units from its star. If this object is real, and not just an error in measurement, a year there would span roughly 5 Earth days, and its surface temperature would hover around 280 Kelvin, or a mild 7 degrees Celsius, though its actual existence is still highly debated and awaits further proof. For more than a century, radio signals from Earth have been reaching the Alpha Centauri system. However, traversing the 40 trillion kilometers of cosmic emptiness that lies between us is an insurmountable challenge with today's technology. Light itself requires over 4 years to cross this void, but for humanity, the journey would demand tens of thousands of years, even aboard our most advanced spacecraft. Advanced technologies could theoretically shorten this travel time considerably. Since the beginning of space exploration, many designs for spacecraft capable of crossing interstellar distances have been conceived, yet none have ever been built. While most of these ambitious missions never progressed beyond the drawing board, one project, Breakthrough Starshot, remains active. This initiative aims to dispatch 1,000 microprobes to Proxima Centauri, propelled by a light sail pushed by an immensely powerful ground-based laser. Calculations suggest these probes could exit our solar system at about 20% of the speed of light, making the trip in approximately 20 years, with another 5 years needed for any data gathered to travel back to Earth. By galactic measures, the area of space immediately surrounding our solar system is not densely packed with stars or other cosmic bodies. Despite this, we have already identified about 50 star systems within a 15 light-year radius of Earth. This collection includes both solitary stars and systems with 2 or more components, bringing the total star count in this region to 65. A great number of them host exoplanets and are surrounded by gas and dust protoplanetary disks where new worlds are still taking shape. To explore all of this, you and I would need to chart our immediate cosmic surroundings, venturing progressively farther from our homeworld across tens of light-years of empty space to visit a multitude of distant systems. Now, let us begin our journey to the stars. Traveling 6 light-years from the Sun, you arrive at our first destination, Barnard's Star, also catalogued as Gliese 699. This star is famous for its astonishing speed across the night sky, capable of traversing a distance equal to the Moon's diameter in merely 180 years, a phenomenon caused by its closeness to Earth, combined with its exceptionally rapid proper motion. Barnard's Star is currently hurtling toward our solar system at a velocity of just over 100 kilometers per second, and is projected to make its closest pass to the Sun in roughly 10,000 years. At that future date, Barnard's Star will become the nearest star to us, with the gap between it and the Sun shrinking to only 38 light-years. Even at that reduced distance, however, the faint glow of this red dwarf will remain too dim to be seen without the aid of optical instruments. This star possesses just 17% of the Sun's mass and has a radius that is only about 1/6 as large. True to its red dwarf nature, Barnard's Star is relatively cool, with a surface temperature of only 3,134 Kelvin, or slightly under 2,900 degrees Celsius. Considering these characteristics, it is hardly a shock that the star's luminosity is 2,000 times less than that of our own Sun. In 2018, a study was released detailing 20 years of observations of the star's motion, which presented strong evidence for a nearby exoplanet. The existing calculations suggest it is a cold super-Earth, possessing a mass at least 3.2 times that of our own planet. This world, designated Barnard's Star B, orbits at a distance of about 0.4 astronomical units from the system's center, completing one full revolution around its star every 233 days. Regrettably, the orientation of this exoplanet's orbit means it does not transit or pass between its star and Earth from our perspective. This alignment makes it nearly impossible to perform a spectral analysis of the object to study its atmosphere. Consequently, scientists must rely on mathematical modeling to infer any information about this intriguing but elusive world. Given the faintness of Barnard's Star, its planetary companion is exposed to 50 times less energy than Earth receives from the Sun. Consequently, the temperature on this celestial body's surface is incredibly low, resting at just 105 Kelvin, or negative 168 degrees Celsius. Nevertheless, there remains a possibility that tidal forces or internal radioactive decay generate sufficient heat to sustain a subsurface ocean. If such an ocean exists, any potential life within its depths would have had ample time for gradual evolution, since Barnard's Star, at over 10 billion years old, is one of the most ancient stars known. Thanks to its relative closeness and advantageous trajectory, Barnard's star stands out as a high-priority destination for a prospective interstellar mission, although whether human-made spacecraft will ever make the journey is still uncertain. Meanwhile, on the opposite side of our Sun, you can find a stark contrast to the dim red Barnard star. Sirius. Located just 8.6 light-years from our world, it is the most brilliant star in the night sky. While it may look like a single point of light, closer observation has revealed that Sirius is not one object but a binary star system. The two component stars are currently at their greatest separation, orbiting each other at a distance of about 30 astronomical units. The primary star, designated Sirius A, is a luminous blue-white star that is 70% larger in diameter than the Sun and has a surface temperature of 9,940 Kelvin. This intense heat causes it to radiate 25 times more energy than our own star. Its partner, known as Sirius B, is almost invisible against the glare of its massive companion. Sirius B is a white dwarf with a radius of approximately 6,000 kilometers. Yet its mass is nearly identical to that of the Sun. True to its classification, its surface is exceptionally hot, at 25,000 Kelvin. But its diminutive size renders it about 10,000 times fainter than its stellar partner. After prolonged and dedicated searches, astronomers have found no evidence of planets within the Sirius system. This absence might be explained by the system's youth, or the specific alignment of its ecliptic plane, which prevents planets from being detected via the transit method, as they do not pass between their star and Earth. An alternative theory posits that around 120 million years ago, Sirius B used up its nuclear fuel and expanded into a red giant. Shortly after, it ejected its outer layers, transforming into the compact, intensely hot white dwarf we see today. This explosive event would have obliterated the young system's protoplanetary gas dust disk, scattering its remnants into space and eliminating any chance for developing planets to survive. At present, both stars in the system follow moderately elliptical paths around a shared center of mass, taking 50 years to complete one full orbit. For the next 60,000 years, Sirius will continue its approach toward Earth, growing even brighter in our night sky. It will reach a minimum distance of about 7.5 light-years before it starts to slowly recede from us. This retreat will continue for another 660 million years, after which the luminosity of Sirius will begin to wane, and within a few months, the star will vanish from the sky for good. Leaving the vicinity of Sirius, which bathes its surroundings in ultraviolet radiation and stellar wind, we can navigate toward a Sun-like star situated 11 light-years from Earth. This star appears in various catalogs under different designations, including Wolf 1061. It is a red dwarf with a radius about 30% that of the Sun, and a mass roughly 4 times smaller than our star. Its surface temperature is 3,272 Kelvin, which is about 2,970 degrees Celsius. Like other stars of its type, Wolf 1061 is incredibly faint, with a luminosity just 0.1% of the Sun's, making it invisible from Earth to the naked eye. Despite its dimness, this red dwarf hosts one of the most populous and varied planetary systems among our nearest stellar neighbors, with 3 confirmed rocky exoplanets. The environments on these 3 worlds are markedly different from one another. The first and innermost planet is Wolf 1061b, which orbits at a distance of 0.038 astronomical units and completes a revolution in just 5 days. Its mass is estimated to be between 1.5 and 2 times that of Earth, with a radius 20% larger than our planet's. It is highly probable that this world is tidally locked, always presenting the same face to its star, which results in extreme temperatures on its illuminated side and renders it completely uninhabitable. The system's second object, Wolf 1061c, orbits at a distance of 0.089 astronomical units, finishing its year in approximately 18 days. This places it squarely within the star's habitable zone, marking it as a potentially life-supporting world. As a super-Earth, Wolf 1061c is about 3 to 4 times more massive than our planet, with observations suggesting its radius is around 1.6 times that of Earth, and its surface gravity is about 1.3 times stronger. The exoplanet receives considerably less energy than Earth, leading to a much lower equilibrium temperature of 223 Kelvin, or about negative 50 degrees Celsius, which is slightly warmer than Mars. Of course, for liquid water to exist amid significant daily and seasonal temperature swings, a planet needs a dense atmosphere with a strong greenhouse effect, which could potentially create more temperate conditions. However, the system's third planet, named Wolf 1061d, follows a distinctly elliptical path. Its orbit takes it as far as 0.73 astronomical units from its star, before swinging back into a much closer distance of just 0.21 astronomical units. Calculations show that this world completes a full circle around its star in 67 days. This planet's mass is estimated to be approximately 7.7 times that of our own. If it is a rocky super-Earth, its radius would be about 1.7 times larger than Earth's. But if it is a mini-Neptune with a dense, layered atmosphere, its diameter would be at least 2.2 times greater. However, even with its highly eccentric orbit, Wolf 1061d consistently remains outside its star's habitable zone, making it an unlikely candidate for life. Nevertheless, the planet holds considerable scientific value for understanding planetary evolution, and this system is a high-priority target for upcoming studies. Another fascinating aspect of the star Wolf 1061 is its position right on the fringe of what is known as the local interstellar cloud. This is an expanse of space suffused with hot, though incredibly thin, hydrogen gas, reaching temperatures of roughly 7,000 Kelvin. The density here is remarkably low, averaging just 0.3 atoms per cubic meter, about half the typical density found throughout the Milky Way galaxy. For the last 10,000 years, our own solar system has been journeying through this very cloud. Spanning an average of 30 light-years in diameter, the local interstellar cloud is vast. Yet our system finds itself situated near its boundary. To give you some perspective, our closest stellar neighbor, Alpha Centauri, has already crossed into the adjacent G cloud. Our trajectory indicates we will continue through this cloud for another 2,000 years, before transitioning into an even more rarefied region of space. This particular area is believed to have been created by the impact of 2 massive bubbles of hot interstellar gas, giving it a unique momentum, magnetic field, and radiation profile. Despite the highly energetic nature of the particles composing the cloud, you can be assured that life on Earth faces no significant danger from them. Our planet is well shielded. The solar wind effectively deflects the cosmic hydrogen, while our dense atmosphere neutralizes any particles that manage to breach the heliosphere's defenses. Interestingly, scientists have discovered traces of the iron-60 isotope, or interstellar iron, preserved in ice, which is thought to have been deposited on Earth during our passage through the local interstellar cloud. As we press onward through the cosmos, our next point of interest is a highly peculiar star called AP Columbae, situated 270 light-years away. Its most striking feature is its incredible youth. It formed just 40 million years ago, a time on Earth when the dinosaurs were already long gone. What makes its location so surprising is that stars typically spend up to several hundred million years within their native stellar nurseries, a period far longer than AP Columbae has. An analysis of AP Columbae's movement suggests it was once part of the open cluster 1C2391, a family of about 30 stars sharing a common origin and trajectory. This arrangement was shattered millions of years ago when one of the cluster's stars exploded, violently disturbing the delicate gravitational equilibrium. That powerful event imparted a significant boost to the young star, effectively flinging it away from its stellar home at high speed. Although AP Columbae is a tiny red dwarf with a mass just 13% of our Sun's, it radiates more energy than any other known star of comparable parameters. Furthermore, its radius measures double what contemporary theories of stellar structure predict for an object of its type. Remarkably, the key to solving these puzzles was found in a spectral analysis of its light, which revealed the presence of lithium in its stellar material. While lithium is common in the clouds that form stars, it is rapidly consumed once nuclear fusion begins. This discovery confirms that AP Columbae is an extremely young, still forming star that has not yet settled into its main sequence phase of life. This youthful state explains its volatile and explosive behavior, which includes massive ejections of material that can cause its brightness to surge by a factor of 10. Typically, such violent outbursts would be devastating for any nearby exoplanets, as they can strip away atmospheres and sterilize surfaces with intense ultraviolet radiation. Yet, observations have confirmed there are no large celestial bodies orbiting within 4.5 astronomical units of AP Columbae, as the star is simply too young for fully formed planets to have taken shape. Despite this, it remains an extraordinary object, providing invaluable insights into the early stages of a star's life cycle. As you have just seen, not every star is accompanied by a system of planets. With that in mind, our final destination is the orange dwarf star Gliese 370, located 37 light-years away. It was here that, in 2011, astronomers identified a lone exoplanet named Gliese 370b. Detected via the radial velocity technique, this world is estimated to have a mass between 3 and 4 times that of Earth. Based on current models, it is likely a lava planet with a radius approximately 30% greater than our own, where the surface gravity would be at least 40% stronger than what you experience on Earth. Positioned at a distance of 0.26 astronomical units from its star, the exoplanet Gliese 370b moves swiftly, completing its yearly journey in just 54.4 Earth days. This orbit places it firmly within the star's habitable zone, and if its surface reflects light similarly to Earth, its average temperature would settle around 25 degrees Celsius, slightly warmer than our own world. Crucially, its distance from its sun suggests it isn't tidally locked, which means it likely possesses its own day-night cycle, a key factor for distributing heat evenly and fostering a stable climate. The planet's moderately high gravity would probably result in a smoother, less mountainous terrain, which, combined with a potential abundance of liquid water, could give rise to expansive, warm, shallow oceans. Environments like these have long been considered ideal cradles for the emergence and evolution of life, which is why Gliese 370b was once seen as a prime candidate for hosting living organisms. However, more recent research has painted a slightly less inviting picture of the conditions on its surface. There is now a significant possibility that the planet is shrouded in an extremely dense atmosphere, triggering a powerful greenhouse effect. Despite this, even the most conservative models suggest the average surface temperature doesn't surpass 78 degrees Celsius, creating a thermal environment that ranges from about 30 to 100 degrees. Given that our own planet experienced a similar climate during its Archean period, Gliese 370b remains a highly compelling target for ongoing and future searches for extraterrestrial life. If you step back and consider our journey, you'll realize we have ventured more than 50 light-years from the solar system. This region of space is populated by over 1,000 stars, most of which are solitary wanderers, while others are bound in binary pairs or even form complex stellar families. The most striking example of such a group is Castor, an astonishingly intricate system made up of 6 individual stars. Located 50 light-years from Earth, the Castor system is visible to the naked eye as what appears to be a single brilliant star. It has been known to humanity since ancient times, recognized as the second brightest point of light in the constellation Gemini, and the 23rd brightest star in the entire night sky. Its complex structure is due to its 6 distinct components, which are organized into a sophisticated gravitational dance. The 2 most luminous members, Castor A and Castor B, are blue-white stars, resembling Sirius, and each is accompanied by its own close companion, a red dwarf. The centers of these 2 binary pairs are separated by about 110 astronomical units, and they take 445 years to orbit each other. Farther out, another pair of stars orbits this central quartet. At a distance of approximately 600 astronomical units from the main group, you will find a third close binary system, composed of 2 very similar red dwarf stars. Each of these dim stars has a mass of about 0.6 times that of our Sun, and a surface temperature of around 3,000 Kelvin. They are so close to one another that they complete a full revolution in under 20 hours, while their shared orbit around the entire Castor system's center of mass is a highly elongated ellipse that takes roughly 14,000 years. To date, no confirmed exoplanets have been found within the Castor system, but if they do exist, the most probable location would be around its dimmest components. For instance, back in 2018, astronomers observed fluctuations in the orbital timing of Castor C, hinting at the presence of a nearby brown dwarf, approximately 49 times more massive than Jupiter. According to calculations, this object would orbit its parent stars at a distance of 4 astronomical units, taking 54 years to complete its circuit. Much like many other red dwarfs, the stars of Castor C could host rocky exoplanets in close orbits. If such a world exists, its sky would offer an incredible spectacle, dominated by 2 crimson suns, brighter than our own moon, perpetually circling each other. For now, however, whether such a vista truly exists remains beyond our ability to verify. Despite the immense distances between the stars we have explored, they are all part of a single vast structure known as the local bubble, which spans about 300 light-years and contains several smaller structures like the local interstellar cloud. This enormous cavity was carved out by a series of supernova explosions that occurred between 10 and 15 million years ago. The local bubble is essentially a giant expanding cloud of interstellar gas, superheated to 1,000,000 Kelvin, causing its density to be about 10 times lower than the galactic average. This hot, ionized hydrogen constantly emits X-ray radiation, but thankfully, the magnetic fields of the Sun and Earth, along with our planet's atmosphere, provide effective protection from this potentially lethal cosmic weather. Our local bubble is not isolated. It shares borders with other, similar formations. For example, slightly offset from the solar system's path lies the Antares bubble, which was also created by supernova events near the star Antares. The long-term interaction between these two cosmic structures has led to the formation of massive condensations of gas and dust in the boundary region, which the solar system is projected to reach in about 50,000 years. We find ourselves surrounded by an incredible diversity of stars, whose light provides warmth to countless planets. Exploring these distant worlds would be impossible without the aid of modern spacecraft and powerful telescopes. It is only through these instruments that our vision can traverse the immense voids of space, allowing us to glimpse the most remote corners of the universe. With every new observation, the cosmos reveals another of its previously unknown facets, never failing to astonish us with its sheer grandeur.